while I'm here with the speaker and with this device called a function generator, which can generate a sine wave of whatever frequency I like, let me just illustrate for you what happens when we play an adjustable frequency sound out through this speaker so you can hear it for yourself. I have the amplitude, the volume turned way down, so let me turn the amplitude up a little bit. So this is 880 hertz, so that is known as A5 on a piano. Let's go down to 440, and that'll be A4 on a piano. Okay, so that's 440, which is known as A4 on a piano. And then we could go down to 262, which is known as C4 on a piano, or middle C. Sine, triangle, square. What I was just playing for you a moment ago were a sine wave and a triangle wave and a square wave of a given frequency. So frequency is a fundamental idea for vibrations, for waves, for sound. To your ear, frequency corresponds to pitch. For a vibrating object like a pendulum, frequency is the number of cycles per second. Mathematically, frequency is a parameter of a sine function, like 2 pi ft. So the f and 2 pi ft is the frequency. So motion that is purely sinusoidal, also known as simple harmonic motion, contains only a single frequency. So the sine function represents a kind of a building block, a kind of simplicity in describing things that are periodic. So there's this amazing math result, I think it's a Math 240 result, called Fourier's theorem, that tells us how to build up more complicated functions by adding up sine functions of different frequencies. For example, you can build up a square wave that repeats itself once every t seconds by adding up sine of 2 pi time over big T for period. So basically, frequency f plus 1/3 of frequency 3f plus 1/5 of frequency 5f plus 1/7 of frequency 7f. So 110 hertz square wave is the same as 110 hertz sine wave plus 1/3 of a 330 hertz sine plus 1/5 of a 550 hertz sine, and so on. So I'm just graphing here the first term, then the sum of the first two terms, and the sum of the first three terms, and so on. You can see once you get to like 5 or 6 terms, you get a pretty decent square wave. So a square wave is actually just made up by building up different sine waves, f, 3f, 5f, 7f. But for the square wave, you take f with full amplitude, then it's 3f with a third amplitude, 5f with a fifth amplitude, 7f with a seventh amplitude. By contrast, if you go to the triangle wave turns out to be f with full amplitude, and then 3f with 1/9 amplitude, actually opposite sign, but minus 1/9 amplitude. And then you have 5f with 1/20 amplitude, and then 7f with minus 1/49 amplitude. In the case of the square wave, we had f, 3f, 5f, 7f, and the coefficients go like the harmonic down to their single power, so like 1/3, 1/5, 1/7. In the case of the triangle wave, it's 1 and then the square of 1/3, and then the square of 1/5, and then the square of 1/7. So what that means is, so if you take the sine wave all by itself, I guess you can see on the blue curve here, there's only one frequency. If you take the square wave, you have the higher frequencies, and the higher frequencies have, their weights die out pretty slowly, like 1/3, 1/5, 1/7. If you take the triangle wave, the higher frequencies weights die out much more quickly, 1/9, 1/25, 1/49. Then when you play the tone, when you hear the sine wave, it sounds like a nice pure tone. When you hear the triangle wave, you can hear the overtones, but not too harshly. When you hear the square wave, you hear the overtones pretty harshly because the overtones in the square wave have a much larger relative proportion than those same overtones do in the triangle wave. You don't really need to remember this, but it's kind of an interesting fact. You can hear the difference between a sine, a square, and a triangle. So the sine sounds like kind of like a flute or woodwind instrument. The square has that really harsh sound of like a 1980s Atari video game. And the triangle is somewhere in between. In the triangle, you can hear the overtones, but not with quite so much volume. These are different waves. That sine wave you heard, the triangle wave, and the square waves, they're the same fundamental frequency, but they have different mixtures of overtones. And different mixtures of overtones are one facet of what you would call timbre, or tonal quality in a musical instrument. What makes one musical instrument sound different from another musical instrument playing the same frequency? It's kind of how much of the different frequency content do you get? I mean, there are other details too, but that's a significant part of it.
What I'm doing here is driving one end of the wave machine with a periodic generator, a little motor going up and down. This end of the wave machine is clamped, it's immobilized with a big mass. So this isn't moving. We have a pretty good node right here. This point isn't moving. There's a decent node here, so this isn't moving. And then the far end is moving just a little bit because that's where we're driving it from, but that's a pretty tiny amplitude. So there's basically a zero, maybe a little beyond the end here, approximately the end, and here, and then at this far end. So we have 3 half wavelengths. There's 1 half, 2 half, 3 halves. We have 3 half wavelengths fitting on a tiny bit more than the full length of the wave machine. Now let's see if we can do something quantitative with that. The first thing we want to know is how long is the wave machine. The full length of the wave machine is 1.73 meters. The frequency we're driving it at is 0.61 hertz. We have 1.5 wavelengths fitting on the whole length of the machine, and the wavelength must be 2/3 of the length of the machine. It's 1.15 meters wavelength. Now let's disconnect the little motor and see if we can figure out how long it takes a pulse to go back and forth. We're going to say, how long does it take a pulse to go from this end all the way down there and back? Okay, that was about 5.5 seconds. Let's try it again. That was about 5.25 seconds. Let's say it takes about 5.3 seconds to go 2 lengths of the wave machine. So that gives us a wave speed on this machine, about 0.65 meters per second. The calculator says 0.70 meters per second. And we got 0.65 meters per second. That's like within 10%. Not bad. It's a pretty high frequency right now for this wave machine. This is 3.6 hertz, 3.6 cycles per second. And at the other end, way down here, what's making all this dinging noise is I have a little dash pot here. So wavelength equals wave speed divided by frequency. So if we make this frequency smaller now, we should get proportionally larger wavelength. This is 3.6 cycles per second. Let's go to about 1.8 cycles per second. That's pretty good. I think we have a wavelength that's something like that now. So let me go down to 0.9 hertz and see what we see. Now that should double the wavelength again if we can get it to stabilize. I think I see a wavelength about like that. And then let me do this now by hand. So I can go like that. That's pretty good. So now let me try doing that about twice as fast. Yeah. So you see about half the wavelength. And let me try going about a lot slower. That's not bad. So that's a pretty long wavelength with a low frequency. And then I'll go a little faster. And you can see the wavelength gets smaller. And I'll go faster yet. Higher frequency. You can see the wavelength gets smaller yet. I'll try to go about twice as high in frequency. Let me see. Yeah. So I think that's pretty believable that the wavelength is inversely proportional to the frequency. So finding the standing wave patterns for a pipe that you blow air in is a little bit trickier than the standing wave patterns for a string because, well, there are 2 common cases. One is a pipe that has both ends open. Like here's an example. So this is open. And then the end that I blow in is also open. Actually, in this case, the pattern is similar to what you get with a string, except that it's kind of the opposite in that the displacement can be maximum on the end I'm blowing at, and the displacement can be maximum on the open end. But then 90 degrees out of phase with the displacement pattern is the change in pressure pattern. And the pressure with respect to atmospheric, the change in pressure with respect to atmospheric is 0 at the end here. So we just get atmospheric pressure here. And then at the other end, this other open end, the change in pressure with respect to atmospheric pressure is 0. But you can have a maximum pressure excursion here in the middle scale where the displacement is changing most rapidly. In this case, you get half a wave fitting in the complete length of the tube for the lowest frequency, and then you get multiples of that. So you can have the length is a half wavelength, the length is one wavelength, the length is 1.5 wavelengths, the length is 2 wavelengths, and so on. So here's the pattern of wavelengths you get. So then the frequency, which is the wave propagation speed divided by the wavelength, so you can get wave speed over 2L times 1 times 2 times 3 times 4. So that looks pretty familiar from the guitar string. And you can also see that the lowest frequency you get is inversely proportional to the length. So if I have two very similar tubes, so they look the same, but one is bigger. So this is the bigger one, here's the smaller one, but they have the same basic shape. So you expect the smaller one to give you a higher frequency, the bigger one to give you a lower frequency. Makes sense from the formula because the length is downstairs here. It also makes sense from intuition because you know a mouse makes a higher pitched sound than a lion. In both of these cases, both ends are open. The end that I blow in is open, and you can see that this far end is open. So in this case, the allowed patterns are that half a wavelength, 1 wavelength, 1.5 wavelengths, 2 wavelengths fit into the full length of the flute. The fundamental frequency is the wave speed divided by twice the length. So this is a familiar result from the guitar string. You'll notice that these two are similar, except that this one's about twice as long as this one. I claim that this one is going to play a note which is about an octave higher than this note because this frequency is going to be about twice as high because you have the wave speed divided by 2 times the length. So the length is downstairs. So if you double the length, you'll half the fundamental frequency, or if you half the length, you'll double the fundamental frequency. Let's try sounding both of these things. So here is the smaller one, and here's the one that's about twice as long. I think if I blow it hard, you can hear the overtones. And the overtone from this one sort of starts to sound like the fundamental from this one. Which I think kind of makes sense because you expect the next overtone to be double the fundamental frequency. But, okay, there's the fundamental from the short one. Fundamental from the long one. And again, if I blow hard enough to get some overtones too, you can hear that the next dominant overtone is about an octave higher. Let's look what happens when instead we have one end closed. So the end that I blow in is still open, but I've capped off the other end. So it kind of looks like this. So in that case, at the end that I blow in, the displacement or velocity can be maximal, but you have a displacement node, also known as a velocity node. So the displacement is always 0 at the far end because there's this obstacle preventing me from displacing the air over there. But the pressure at the end that I blow in stays at the ambient atmospheric pressure. But at the far end, I can have a maximum pressure excursion. So what you see here is a quarter wavelength fitting in the length of the tube in the lowest allowed mode. And then the next mode after that is where, you see if I just look at the pressure wave, here's a 0 and here's a maximum. So I could say, well, 0 and then maximum, and then it goes through 0 again and then a minimum. In this case, I have 1/4 of a wavelength fitting in the length. And the next mode up would be 3/4 of a wavelength fitting in the length. And the next mode up would be 5/4 of a wavelength fitting in the length. So it's a sort of 1, 3, 5 pattern instead of the 1, 2, 3 pattern for the fundamental mode and then the overtones. But in any case, what you see is that for the lowest mode, and the lowest mode is the note that you sense that I'm playing, is the wave speed divided by 4 times the length, whereas for the both ends open case, we had the wave speed divided by 2 times the length. If I want to play the same note with the both ends open versus a one end closed, to get this frequency to match this frequency, this length would have to be twice as big. So it seems like with the one end closed case, I can have half the length and get the same frequency. This is the one end closed case. This is the both ends open case. So in both cases, the mouthpiece is open, but for this one, the far end is open. For this one, the far end is closed. And the place where it's closed off is right about here where my thumb is. So you can see it's plausible that it's a factor of 2 from here to here versus here. Let's see what happens. Seems like the same note. So the one that has both the mouth end and the far end open has to be twice as long to get the same frequency as the corresponding note for the one that has the mouth end open and the far end closed.
I happen to have in my hand two pipes, both of which have one end open, one end closed.
The length of this one is 1.5 times the length of this one. You expect to see this one to be higher in pitch than this one by a fifth. Something like going from C to G. This thing allows me to make a water column, and you can see it's marked out in notes. C, D, E, F, G, A, B, C. So I think I can bring the water level up to here, and then up to here, and then up to here, and so on. Let's see how that goes. Could be worse. We have here a column of air. You can see the green level of water here, and then you can see this white PVC pipe. And by moving this pipe up and down, you can see where the water level is. The column of air inside this narrow pipe that I'm holding in my right hand has a length that you can see from the top of the pipe to the water level. So you know that if you can see the water outside the pipe, the water will be at the same level inside the pipe where you can't see it. Depending on how long we make it, it'll resonate at a different frequency. For instance, when you have a pipe which is open at one end and closed at the other, the fundamental frequency, the lowest frequency you can get, is where the wave has a minimum here and a maximum here. So it's a quarter of a wave fitting in the length. And I think I drew this on the board over here. So the fundamental mode, the lowest frequency mode you can get with a pipe which is closed on one end and open on the other, is that 1/4 of a wave fits there. We know the speed of sound in room temperature air is 343 meters per second. And I happen to have here a tuning fork which is tuned for 341 hertz. It turns out to be F4. That's convenient. So 341 hertz is pretty much the same number as 343 meters per second. So then the wavelength is right about 1.0 meter. So then 1/4 of a wavelength would be 25 centimeters. So let's see what happens when we adjust the length of this tube until it's pretty close to 25 centimeters too. So from the top of the PVC tube to the top of the green water level, you can see is about 2.5 stripes. Each stripe is 10 centimeters, so that's about 25 centimeters. Seems like the best resonance is when we're right around 25 centimeters. Now we should be able to get a pretty good resonance also at 75 centimeters. Let's listen for it. Yeah, there's another pretty good resonance up there. And then if we look, here's 5, 6, 7, 7.5 stripes. We've got one pretty good resonance when the length of the tube was 25 centimeters. The length of the tube was 1/4 of a wavelength. And then we got another pretty good resonance when we lengthened this so that the length of the air column, in other words, from the top of the tube to the top of the green column of water, was 75 centimeters. So then we saw that the length of the column of air was 3/4 of a wavelength. Now, let's try something very similar. This is 341 hertz, so that's the F above middle C, so that's F4. This is 262 hertz, 261.6, 262 hertz. This is middle C. So let's try with middle C. So middle C, I worked this out on the board, has a wave, so it's 262 hertz, has a wavelength of 1.3 meters. So then a quarter of a wavelength would be 33 centimeters. And that's pretty good. That seems to be, there's 1, 2, 3, just a little over 3 stripes. That seems about right. So I could believe that's about 33 centimeters.
So it turns out that there's a professor at Penn State University that has some good animations of longitudinal waves. And remember, longitudinal waves are quite a bit harder to visualize than transverse waves. You often see graphs that look like these blue graphs with the red traces in textbooks, and it's hard to interpret those, figure out what the motion of the constituent particles in the wave really looks like. Professor Russell from Penn State decided to make an animation to try to make it a little easier for you to see that. So here you see a piston moving back and forth on the left-hand side, and this is a pipe which is basically open on one side and closed on the other. You can see that there's a velocity or displacement node on the right side because it's a closed right end. There's a pressure antinode corresponding to that velocity node, and then you see on the left side where the piston is, there was a pressure node but a velocity antinode. On the top left, you see the lowest possible frequency. What's the fundamental frequency, standing wave pattern for a pipe which is closed on the right, open on the left. So you can see a quarter wave fits in the top left case, then 3/4 of a wave fits in the top right case, and then we go down, and in this case 5/4 of a wave fit, and in the bottom right case 7/4 of a wave fit.
You can make an analogy between an organ pipe. Let's say it's an organ pipe where both ends are open, and we make it resonate, and there's air inside resonating, so the medium is air, whereas over here we had a string, both ends of the string are anchored, and we're looking for standing waves, and we have some tension, and we have some mass per unit length. So if we have sound waves in an organ pipe, instead of tension divided by the mass per unit length of the string, that same square root is replaced instead by the bulk modulus, which is the elastic modulus of the air, divided by the density of the air. Or essentially what you can see, replacing the mass per unit length of the string, we have the density of the air. Now the density of ordinary air is proportional to the mass per molecule, or mass per mole of molecules, of the constituents of air. Air is about 80% nitrogen, which is N2, about 21% oxygen, which is O2, and then there are trace amounts of other things like argon and CO2 and so on. So anyway, nitrogen, about 28 grams per mole. Now what if we replace the nitrogen with helium? So helium is about 4 grams per mole, because a helium nucleus is 2 protons, 2 neutrons. If the downstairs in that square root goes from 28 to 4, then that's making the downstairs a factor of 7 smaller, so it's making that whole square root of the inside of that square root a factor of 7 bigger, and the square root of 7 is kind of 2.5, a little less than 3. So each one of my resonant frequencies, let's say of my windpipe, should be about 2.5, 3 times higher if I breathe helium instead of breathing air. So let's give it a try. Toreador en garde. Let's see what happens if I fill my lungs with helium. Toreador en garde, toreador, toreador. Songe bien, oui, songe bien en combattant. I should really get the helium out of my lung. Yeah. According to the calculation, it should be like about 2.5 times the pitch if I breathe the helium and sing the same thing. When two waves going opposite directions meet, they pass right through one another, but their amplitudes add. So if you have two waves meet where they're both peaks, then when they meet, you'll get a bigger peak. And if you have two waves meet where one is a peak and one is a trough, when they meet, they'll add to 0. So when two waves meet and they have the same phase, they're either both up or both down, that's called constructive interference, and the result is a bigger wave. If two waves meet and one is up and one is down, then that's called destructive interference, and they cancel one another out. This tone that you hear, it's 880 hertz, so it's A5, the A above middle C. The speed of sound in room temperature air is 343 meters per second. A frequency, a wave of 880 hertz frequency in room temperature air has a wavelength, speed of sound divided by frequency, wavelength of 39 centimeters. We're going to measure this tube here, and you'll see that there's a speaker down here, and then there's a microphone up here. The wave that comes out of this speaker, the tone that comes out of the speaker, can take two paths. There's the left-hand path, or there's the right-hand path. And how long are those two paths? If we look at this path, this is 80 centimeters, that's another 40 centimeters, and that's another 80. So that's two waves, one more, and then 2 waves. 2 plus 1 plus 2 is 5 total wavelengths. I come over and I look at this side, it's going to be the same thing initially. There's 1 wavelength, 2 wavelengths, 3 total wavelengths, and then 2 more, that's 5. So I kind of drew that over here. So the left path, here's 2 wavelengths, 1 wavelength, 2 more, that's a total of 5 wavelengths. The right-hand path, 2 wavelengths, 1 wavelength, 2 more wavelengths. But this side is adjustable. So we could make this, say, 2 1/4, and then 1 and 2 1/4. So then instead of a total of 5 on the right side, we'll have 5 1/2, or so on. If I change this length by 10 centimeters, I'm simultaneously changing this length by 10 centimeters. So I'm changing the total path length here by 20 centimeters, which is half a wavelength. So every time I move this by 10 centimeters, so this is 10 centimeters, going from constructive to destructive interference, or then from destructive back to constructive interference. First, it's as if you were sticking your ear in there. Your ear will be my microphone. Now let's watch it on an oscilloscope. So an oscilloscope is a way of displaying visually an electronic signal. So we can display visually the electronic signal that comes out of this microphone. So we'll put Mr. Microphone in here, turn the amplitude up, the volume. And now you see 2 waves on this oscilloscope. The bottom signal is being played out by the speaker on the bottom. The top signal is being picked up by the microphone on the top, and you can see they're both about the same size right now. Now I'm going to decrease the right-hand path by half a wavelength, and we'll see what happens to the top trace, the microphone. See, and you can see that this trace is now just about flat, so it's a much smaller amplitude. We'll go back out to the original length. So I changed this length by 10 centimeters. That changes, of course, this length by the same. So it changes the total path length by 20 centimeters. So now it's loud again. You can see the big wave here. And we'll go and make this another 10 centimeters bigger, and it'll do the same thing on the bottom since they move together. And so that should be destructive interference again. And indeed, we see the nice flat waveform. And then we'll go out another 10 centimeters. And this should be constructive interference again. And indeed, you see the big wave there again. Neat.
So I made a little animation to do the same thing you saw in that previous demonstration. So you imagine that the speaker is on the bottom and that the microphone is on the top. And the wave is emanating in both directions from the bottom. And then in the case where they reach the top, they go the same path length left and right. So you see that the ball going up and down, which reflects the sum of the 2 waves, is waving up and down with a big amplitude. And then I can make one of the paths a little shorter than the other by moving this slider. You see now they're basically out of phase. I guess I didn't quite get it perfectly out of phase. And I think I can make it even better. Yeah, okay, so that's pretty good. See, I can move it just so then they cancel and the ball stops moving. Oh, that's nice. So then I've got destructive interference between the blue and the red. So the blue ball stops moving. And I guess I can go over here and I can make the path length, one of the path lengths longer again. And again, about just the right, yep, so if I do it just right, then I get nice destructive interference and the little black ball stops going up and down when the red wave and the blue wave arrive just opposite one another and cancel each other out. So that is sort of a visual equivalent of what you just heard and saw.
Here I have two tuning forks, and each one of them is a 440 hertz tuning fork. There's one. There's the other. Oh, and in fact, if I strike one of them, I can actually get this one to keep resonating because they're so close together in frequency that the sound coming out of this one excites the other one. I'll start this one going. I'll stop this one. And this one is still going. Okay, that's pretty good, but that's not really what I wanted to show you. So these are both very, very close to 440 hertz. If I take a tiny little rubber band and I put it on the end of this tuning fork, that additional mass, basically it adds a little bit more inertia. And you know that when things vibrate back and forth, the frequency at which they naturally vibrate back and forth often goes like the square root of some kind of elasticity divided by some kind of inertia. So we're adding more inertia here. So that should lower the resonant frequency a little bit. It should make things go a little bit more slowly because it's adding a little bit more inertia, but it's not really changing the elasticity of this tuning fork. So now, if I strike these two tuning forks, get them both going at the same time, you'll hear kind of an interesting phenomenon called beats. And I can make that even a little more obvious by adding a second, so we'll add a little bit more inertia to this one. So now we'll get this one going and get this one going. Let's do that again. And the analogy for this is you imagine that you are running around a circular racetrack and your friend is also running around a circular racetrack. If you are going around 5 times an hour and your friend is going around 4 times an hour, then you'll lap each other once per hour. And if you're going around 5 times an hour and your friend is going around 3 times an hour, then you'll lap each other twice per hour, and so on. So the beat frequency, the wah, 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 wah beat frequency equals the difference in these two frequencies. This is a bigger difference in frequency, so it's a faster beat frequency. If I change that and make that inertia difference a little smaller, so the frequency difference is a little smaller. Smaller frequency difference means a smaller beat frequency, which means you'll hear it wah, wah less often. This actually is how, in the old days, before the days of electronic piano tuning devices, is how a piano tuner would know if your, if a given note on your piano was in tune. It was by listening to the beat frequency between the tuning fork and the strings on your piano. This is kind of nice because it's just a mechanical device, low tech. But I set up the same thing with 2 function generators, each one connected to a speaker. And this is 440 hertz, 440 hertz. Now let's make one of them be 441 hertz. Now let's make that one be 442 hertz, so 442 and 440. Now let's make it 443. $444. Okay, now let's go back down to 441. Now here's something interesting. I'm going to go from 441 down to 439. Now 438. Now 437. And then 436. So you can only get the absolute value of the difference in frequencies. You can't get the absolute difference in frequency, but you know if you're tightening a string, the frequency of the piano is going up, or if you're loosening a string, the frequency of the piano is going down. So you can tell, okay, I'm getting closer, and you know which one's going up or which one's going down. So then you can figure out the difference by seeing what happens when you change the tension, and a higher tension piano string means a higher frequency. Okay, so that's beats. You can hear the beats.